Hello, welcome to today's webinar on the topic of augmented reality in manufacturing. My name's Christine Perret, and I'll be delivering today's session for you. I want to thank the IEEE Standards Association for hosting today's webinar. This presentation is the sixth in a series of IEEE webinars designed to inform and raise awareness about augmented reality topics in a vendor-neutral manner. Today I'll be sharing with you how manufacturing can benefit from the introduction of augmented reality technology. Some of you watching today will be able to apply what you learn in this webinar to your own processes and address challenges that you face when bringing together technical information with physical world tools and products. Over the next hour, I'll explain why augmented reality is increasingly relevant in the modern manufacturing environment. I will identify and describe manufacturing phases where the human plays an important role, and the presentation of information where there's human can be in context and contribute to faster performance and lower errors. I'll explain some of the techniques in use to pilot AR manufacturing, and I'll close with an analysis of the challenges ahead. Before I get started, I want to go over a few housekeeping items and let you know how you can participate in today's session. If you have joined today's webinar listening through your computer speaker system, also known as voice over IP, then this means you'll be able to hear the presentation without dialing in. If you prefer to call in with a telephone, just locate your audio pane, select Use Telephone, and the dial-in information and access code for today's session will be displayed. You have the ability to ask me questions using the WebEx chat feature. Simply type in your questions to our host, David Stankiewicz, and click Send. At the end of the presentation, David will get to as many of your questions as possible. So now let's go ahead and get started. I'm an independent consultant, and I work on what I call spines, the convergence of space and time. It's very complex, like an ocean of trends, and I build landscapes. On top of those, I start initiatives to fill gaps. I help communities to form so people can communicate and converge, and I provide consulting services. You can find out more at my website. This presentation is part of a series hosted by the IEEE Standards Association. The Augmented Reality in Your Future series has been going on since March, and you can go and play back some of our past episodes. In the beginning, we started talking about the introduction and the basic concepts of augmented reality, the definitions, how people build augmented reality experiences, the use of those experiences in cities and urban environments, and how people make money or spend money in augmented reality. I invite you to go back and view some of those for the basic terminology as well as some of the more advanced fun stuff. Today I'll be speaking about manufacturing. And in order to set the stage for the role of augmented reality, I'm going to speak about some of the current trends in manufacturing. Then I'll introduce some of the thought leaders with whom I've had the privilege of getting acquainted as I've been working towards this presentation, and I'll share the challenges that research continues to work on. So it sounds like manufacturing is an old industry, and in fact it is. We can trace the beginnings of manufacturing to the 18th century. The late 1700s, steam, power, and water made it possible for machines to cut and press and form products. Those were very, very early examples of manufacturing. This went along pretty much unchanged for about a century, until the late 1800s, when it became possible to connect electricity to machines and also to have machines do more sophisticated tasks and form an assembly line so the people could be part of the assembly line and the machines could do their part. Then approximately 40 or 50 years ago, the first introduction of a computer into manufacturing took place. And it took a very long time, but over that third revolution of manufacturing, the latter part of the 20th century, we saw many, many machines introduced into manufacturing. And then about a few years ago, people started calling this new phase of industry, of manufacturing, they call it Industry 4.0 in Germany. And they describe the new generation of manufacturing as having cyber-physical systems, or digital and physical systems that are all communicating with one another in a network and using a lot of what we might think of as Internet of Things technologies, smart devices, smart objects that are communicating in real time to one another. So this is a very exciting new frontier, and that's what I'm going to be speaking with you about today. I want to point out that over time, as these generations of manufacturing have gone forward, the complexity of the products that we can manufacture has escalated. It's just skyrocketed, really. In fact, today, the complexity is very high. Not only the complex products we can make, but the processes that we use to make them are very, very sophisticated. And the diversity of the ways and the kinds of products, the volume of products we make today is unprecedented. We can very quickly make identical units using machines, and then we can also create very, very custom or unique objects using the same workflow and the same manufacturing processes. We also know that globalization has had an effect on manufacturing. The raw materials may be very far away from where the customer is and where the finished goods are finally assembled and distributed to that customer. So this distribution, or the highly distributed nature of manufacturing, is a very exciting trend, partly made possible by 3D printing and some of those other exciting technologies. Overall, this introduction and expansion of information technology into manufacturing is called digital manufacturing, and it's really closely associated with automation. It also means that our manufacturing facilities can remake themselves or be more flexible from one day or to the next, 1 week to the next, sometimes changing the composition or the color of the product that is being made. And in addition, while we can have more sophistication, more customization, we're also reducing costs, reducing errors, and increasing the time, reducing the time to market. In all of this, one of the things that you should keep in mind is how dramatically the roles of people have changed in manufacturing just over the last 20 years and even over the last 5 or 2 years. Increasingly, people who are in manufacturing are very, very advanced in their technology skills so that they can program and manage the tools, the electronic and information tools, and the robots around them. People are filling the gaps where the digital manufacturing hasn't penetrated or where it can't because a human being has to make a decision. So there is still a gap, and this is very much the role of the person. As you can see in the lower right-hand image, this is a person who's working alongside of a machine in doing a task perhaps twice as fast. So digital manufacturing is a very exciting field, but it doesn't solve all the problems for everyone all the time. There are a number of remaining things that we know we need to work on. one of them is that the physical world doesn't always have a digital equivalent or a digital analog. Some tools are entirely in the physical world, and no one has ever created a model that describes that tool perfectly, its shape, its functions, all of its features. And so programming it in the digital world isn't possible. There are also in the physical world many changing conditions, changing temperatures, changing lighting conditions, sounds, vibrations. Those can't be reproduced in the digital world. And the materials that we use and their properties can be worked out in physics and material engineering, but in fact they are not existing and don't always behave the way they're predicted. Another big set of challenges for digital manufacturing is that as we've gotten more distributed, as manufacturing has spread out, if you will, and people are farther from one another, the challenges associated with their data and managing this data so that they can have an uninterrupted communication and collaboration across different links in the supply chain. This is very, very difficult because so many people have different technologies in use. So there's not a technical interchange today. That is certainly on its way. Another thing is you may know what the conditions are and the kinds of products you can make at your facility, but you may not always be aware of the changes at another step in the supply chain. For example, if there's an economic change in another part of the world that could impact the supply of your parts, or perhaps a storm or a medical issue. And so all of these unknowns raise risk, and so people have to make much greater investments in risk analysis. During the manufacturing process, there's also need for people to validate and to make sure that a step was performed, that it was conducted properly and on time and following all of the regulations, perhaps the compliance with processes that have been regulated. We also need to be able to actually certify and inspect the final article that's produced. So these are some of the concerns that we have today. Some of them can be addressed by using virtual reality and have been used. Virtual reality is very valuable for simulation. Simulation plays a role in design and when you're planning the assembly process. When you're manufacturing space design, you're laying out the floor, laying out where the machines are going to go. And when you're training people to do tasks that might be dangerous or expensive to do in the real manufacturing environment. Virtual reality has many benefits, but it also has a great cost. It is complex to set up, maintain, and operate, and it does rely directly on the very important models and the content from the digital world. Furthermore, some people suffer from simulation or simulator sickness because of the vibrations or the disorientation that they feel in a virtual reality environment. So what we've seen over the very recent past is the tendency to combine virtual reality with augmented reality in manufacturing. Augmented reality offers great value where your human being needs to have all of their senses working, all of their physical world acuity. So product prototyping is one of those times when augmented reality can work very, very well, be more faster and more efficient. And especially anywhere in the manufacturing processes where you have very, very complicated procedures or where they are procedures that are done very rarely, they're very, very unusual, then we need to train people or at least be able to provide real-time assistance, telling them when they need to do something, what that step is, and to make sure that the step was completed. And then finally, there's many different kinds of inspections that can be done, and that augmented reality can compare the physical world with the digital models. So I started asking around and doing some study in preparation for this event, and I learned that that manufacturing can be described as having planning and production phases. Now, those two overlap somewhat, so this figure is a little bit simplified, of course. On the far left, I mentioned that there's ordering, and there's a lot of sophisticated and intelligent machines and commerce systems behind the scenes that are working for people to place orders just in time and long time in advance even. And on the far right, there are many other sophisticated systems to make sure that the product arrives at its customer on time and in good condition. So I'm not going to be talking about ordering and delivery technologies. I am going to focus entirely on those that involve the planning of products, the planning of the space in which they'll be made, and their production, and where the human being plays an important role. So what I did here is I created this figure to show you that the human being can be involved more to a greater degree or to a moderate degree. So where there's only one symbol of a human, we can say that that is something where there's a significant amount of intelligence in the technology to do that without the human, but the human is involved. So it's more of a mixture of machine and person. Where there are three symbols of people, that's where humans are really extremely intimately involved in that process. Virtual reality, as I said, has an important role and certainly is useful primarily in the planning phases and the planning steps. And augmented reality is more or less throughout the whole sequence. Now, I just want to point out that the ends of these bars, the red, blue, purple, and yellow bars, are faded out. That's to say that I don't want to communicate that these are hard, cold, and rigid boundaries. In fact, there's a lot of variety because of the diversity I spoke of before. So now I'm going to talk to you about where AR supports people in manufacturing. Certainly in the product design phases, I mentioned a little earlier that we might want to have people reviewing the textures or the size of products in advance, and we could give them something similar to look at or to give feedback about. So I'd like to explain that in automotive, this is now done with some regularity. What's done is that they prepare a physical prototype, approximately the size of the vehicle that's going to be manufactured, and then they also, in parallel on the right-hand side, have the digital model with highly sophisticated features, and a lot of properties are captured there to include reflections and the look of the final product. And by projecting, by doing a digital projection of the augmented reality, of the digital model, using augmented reality on top of this white form, we can then try many, many different styles of models of cars, and we can not only test them for their functionality, their size, but also ask customers their opinions. In the process of prototyping, there can also be some very, very precise measurements that have to be made, and more sophisticated parts have to be modeled. This is also an automotive industry example in which the position of the camera is very, very precisely measured by this arm, this wand that is attached. And this permits us to know the precise position of the object. And so that way the digital model can be overlaid exactly, as you can see on the right-hand side. Now, this is an example of prototyping that it was involved in the door and the assembly and the dashboard and things like that. Here before us is another type of prototyping similar to the product design phase, but much more farther along. So you have an existing automobile, and you'd like to know what a different or new light fixture might look like, or a new fender, how that might appeal or what some of the trade-offs might be. In this particular case, you can see that the screen is mounted on a pedestal, and that pedestal has wheels on it. And the pedestal and the whole configuration here, its position is known in a very, very, very precise way. And on the screen, you can see on the tablet here, you can see that there are many adjustments that could be made and controls, and those could be managing the digital asset and helping the prototyping team better understand the challenges ahead. Now I'd like to talk a little bit more about assembly. Once you've designed the product, or you think you've designed the product, you need to see if it can be built, if it can be built in a way that is efficient. This is a project that was done by the National University of Singapore Mechanical Engineering Department, and what they do is they use augmented reality to simulate the assembly of a product in a couple of different ways. And by giving a real user these digital tools and physical world tools to assemble, they can measure the speed and the number of errors, and they can study the gestures that the person has to make. And this way they can much more precisely estimate the costs and maybe even need to re-engineer the product to have a better, faster outcome. So now suppose you know if you're going to be assembling the product and the product parts that you need, then you might need to go to the factory. And when we start with a factory like this one in the image, it has had changes made to it. It's not a brand new environment. It has had machines installed, removed. And so by using augmented reality, we can see how the digital models line up and how they need to be changed so that they take into account all of the exits and machinery that is in place. When you're doing spatial layout planning with augmented reality, you can count on the manufacturers of those machines and robots to provide 3D models which can easily be used in the factory. So in this photograph, what we have is a real factory, and then people put down a marker, a fiducial, on the factory floor. And then they back up, and using their augmented reality device, their tablet or smartphone or glasses, they can see how the robot will look and whether it's too close or too far away from its neighbor. This can also take a vertical dimension. In this example, when you're trying to design the space that a car will need in the manufacturing space that will be needed in the factory to lower the chassis onto, lower the frame, the body of the car, onto the chassis, then you would need to use augmented reality for simulating that in the real world. And so this is an example that was done a few years ago at Volkswagen. Volkswagen, I'll speak about again, is involved in many of these examples. So sometimes you've now planned the tools that you're going to use, you know how many, the layout of the factory. You still need human beings and machines, and augmented reality can be valuable for configuring exactly where you're going to be putting the machines, and to make sure that in the layout you have the proper clearances for putting escape routes or storing extra supplies and so forth. So this is another way of using augmented reality. The robots, the machines are in blue here. You can sort of make out the markers that are in their place, and this is how we can combine the physical and digital world right up until the time that the machine is installed. And then once the machine is installed, we also need to configure it, to plan how it will be used. And this is the similar configuration screen that you saw a few minutes ago. Using augmented reality here, this is at Volkswagen again, they can program the tasks and the materials that have to be brought, and maybe the tubes that need to be installed in order for the manufacturing process to go uninterrupted. So as you can see in the bottom part of the screen, they're looking at different steps in the assembly process in order to plan correctly. So then with this, we can start to configure the machines. And this is an example from the textiles industry provided by the Tell Me project. In textiles, they change the materials and they change the kind of fabrics that they produce several times per year according to the season. And the machinery may need to be maintained or that may need to be reconfigured. And in that process, what you can also check to make sure that the person who is now working on this machine has received the necessary training in order to work on this particular piece of equipment. You can also find out, get a refresher on what kinds of adjustments to make, what kind of materials need to be installed, and maybe change out some parts and do some maintenance. Similarly, this is a motor that needs to be maintained. It looks like it's overdue for several changes, and so in this example provided by Ingrain, the yellow is just the 3D model that's tracking the physical world in order to be able to provide very accurate instructions to the user during the procedures that they need to follow. So I'm now going to show you a little bit of a video. It's not about manufacturing in textiles or automotive. It's the maintenance of a machine when it is preparing rock for use perhaps in some kind of a process. And these are very, very sophisticated and large size machines. You can kind of see it over there on the right-hand side. This is a feed from the video camera that the man is wearing on his helmet. And you can see that this person is being trained, but he's also probably being certified to use and to perform tasks with this machine. So he's being monitored, and he's going up to the little cabinet so that he can make changes in the electronics or maybe remove something. So in this case, he can use augmented reality right on top of it to verify that he has the right part and to get the in-time instructions. The next step is that, as I mentioned before, human beings are still involved very often in the assembly of products, even sophisticated products such as those that we have being made today. Human beings are involved, and they may need some assistance. So augmented reality can certainly help them to identify the tool that they'll need to use and the parts that they need to assemble. So in this example, very simple use of a tablet, but you might ask yourself, well, if I was holding the tablet, how on earth is he going to be able to perform the procedure? And that's a good question we can come back to later. I think that it's clear that when there are very, very unique procedures that are being taken, then we can have some time to study that process before beginning. But you can also use augmented reality in real time. And this is a video example from Extend 3D that shows that in this procedure, we're going to have a person who's welding and has a 3D model, and there's a projector that is pointing a beam of light, green light, onto the place where that weld has to be done. In this case, he's finished the weld, and he needs to make sure that the hose bib is perfect. And so the 3D model is informing that beam of light, that green light, and as long as there's not a fit, the green light continues to show. So that another example, again in some welding situations, on this part, the beamer, you saw that little projector for a split second, is pointing directly at this part. And now the stud is being inserted, exactly in its position, and it knows that it has been performed correctly. And as you can see, when the part moves, the augmented reality system detects that motion, detects the correct position, and finds the stud again. In this example, we're talking about two very sophisticated parts of a satellite. This is an example used at Boeing, and the satellite's parts come from different places. So we need to make sure that just prior to their assembly, make sure that they will fit perfectly with one another. So in this scenario, the model, or the blue area, the blue, and you can see some gray over on the right-hand side, is overlaid on the physical part. I'm not sure precisely what this part is, and I probably couldn't tell you even if I did, because these are very, very sensitive and secret projects. But you can imagine very easily how, by using the physical world and the digital world, we can make sure that the parts will be well aligned. So once the product has been manufactured or built using a machine or by hand, the next step then is to inspect and to make sure that the procedure that the product fits the design requirements. In this video, I'm going to show you, prepared by Fraunhofer graphics group, there's several things going on. It is a cabinet with some machinery. It could be some kind of an electrical cabinet, or I'm not sure exactly what it is. And there was originally a 3D model, and it is in the lower left-hand corner there. The 3D model is in the lower left-hand, and the actual unit is on the right. And above, we can see where the discrepancy is very high, the red appears. Where there's a very low discrepancy, it's green. Where it's yellow, it's a perfect alignment. So by using depth camera, here no depth camera, and then turning the depth camera back on, the much more precise alignment of the model onto the real world. Very, very important concept, and I hope that we'll see more and more use of depth cameras, such as, in this case, just for prototype purposes, the Connect. So this is showing how, in this case, we can use advanced imaging. Finally, there's continual training. In fact, there's so much training in some cases, in some manufacturing environments, that it's a real burden on those who must participate and those who are constantly revising, reviewing, and remaking the training modules. So augmented reality can certainly help by using and reusing existing models, by reviewing the procedures, by making sure, as you can see in the green arrows there, the purple arrows in this image, reviewing with the person what needs to be done and just how to perform that task. So there are dozens of training examples that we can think of. This concludes the second section of this presentation, in which I'd spoken about all the different stages and gave you many examples of when augmented reality can be valuable to the manufacturing process, mostly to the people in the manufacturing process. Now let's turn to those who are responsible for many of the projects that I just described. These are people who are in universities and academic environments, as well as in businesses, small and large businesses. So the thought leaders that I've had the privilege of coming into contact with include those on this slide. So I'm going to be going over the next few minutes and describing to you what they do and what they're known for, and maybe you can go yourself and find out more. One of the very earliest groups that studied industrial augmented reality, including manufacturing, is the Technical University of Munich's CAMPAR, or the Computer-Aided Medical Procedures and AR chair. Has two groups, one that focuses on the medical procedures and the other one more on the professional augmented reality, including manufacturing. This university and this group in particular, these people, the leaders, this group, have taught and have been involved in many, many projects. In fact, they're responsible for over 50 PhDs in these domains since 2003. The professional AR group itself began in 1997. It's chaired by Gudrun Klinker, who is still doing projects in close collaboration with many companies, including German companies and industrial partners. In Asia, in Singapore more specifically, the National University of Singapore Department of Mechanical Engineering is also a leader in the research and implementation of augmented reality. There is an augmented reality and assisted technology laboratory, several key faculty there, and the group works on integrating VR and AR into manufacturing. They have many, many published articles in the literature, and they've been leading in this field for about 5 or 6 years. You saw a video a little bit ago, and one of the other very important groups that works in augmented reality for manufacturing is the Fraunhofer Graphics Group. It's established in 1987. There are many people who work on other graphics topics, not just augmented reality. I think it is about 25 or 30 people who work on virtual and augmented reality in the Competence Center. They've been working on VR since 1994 and augmented reality now since 1998. Definitely early, and this group and the Technical University of Munich started very, very in close collaboration. The projects that the Fraunhofer IGD has done in manufacturing include, of course, heavy industries like shipbuilding and automotive, and probably many others that we're not privy to. Mataio is a software company that you may have heard of in augmented reality. It's one of the important providers of software solutions, and in the near future is going to also be involved in hardware. They've been conducting applied research in industrial augmented reality since 2003. In fact, Thomas Alt and Peter Meyer, the two founders of Mataio, were students at the Technical University of Munich and did internships and won a grant with Volkswagen in 2003. That was really the origins of the company, and since that time they've done many, many projects. They're also receiving funding from European Union research initiatives and German research projects. So they today provide the Mataio Engineer is a software solution that you can use to introduce augmented reality into your industrial procedures, including manufacturing. There's also a software development kit that a developer can use to create these custom solutions. Ingrain is another small company in Canada, based in Canada. They've been involved in virtual reality for a long time with 3D models. They've done applied research in the field of visual analytics, and they're a member of the Aerospace Industries Association of Canada. They've done a lot of projects in defense, energy, and aviation. They provide some commercial solutions as well. You might want to look at Producer Pro, the Configurator Software Development Kit, and another kit that's called the Virtual Task Trainer. Now I'd like to tell you about this collaboration between the University of Sheffield and Boeing. The Advanced Manufacturing Research Center has been performing research, oddly, on the subject of augmented reality and virtual reality in aerospace and in automotive. They were established as a collaboration, but since that time, over the last few years, they're now open for membership. And so people are joining that, and there's over 25 Tier 1 members involved, including Rolls-Royce and many other automotive Tier 1 and Tier 2 manufacturers. a research project, also focusing on manufacturing. It's about Tell Me project focuses on technology-assisted or technology-enhanced learning in manufacturing environments. This is a European Commission-funded project with academic and industrial partners, and they have a diversity of partners in different industries. The Arvida project started about a year ago, and it has funding from the German Ministry of Education and Research. It is led by Volkswagen, but there are many companies and research partners involved. They have a great deal of history together, as they have done other projects, also funded by the German Ministry of Education and Research. In this project, one of the deliverables or outcomes is going to be the establishment of a highly flexible web-based reference architecture for AR. They're also going to use that reference architecture to demonstrate how you can reuse and exchange different components. There are also many examples of trials and pilots and prototypes in industry, aviation, for example, Boeing and Airbus in collaboration with Rockwell Collins. These companies are working on augmented reality in commercial aviation, defense, and aerospace, also studying the financial side of this introduction of technology. Airbus has been showing what it calls the factory of the future, in which specific tools and processes are done in a specific part of the factory. So maybe the green tasks are done where it's green, yellow, and red. This way you can see very quickly where there are different activities. You've seen a lot of examples of automotive, and Volkswagen and Daimler are very actively using augmented reality, at least in the prototype stages, throughout the manufacturing process. But there's still a lot to do, a lot of significant challenges that I'll be speaking about now. And so those companies and the universities I referenced are working on challenges in 4 domains. But I don't want to give you the impression that just working on one of those problem sets or domains, such as the technology domain or the business domain, can happen alone. All of these areas are interconnected, and that's why a circle very fairly represents the kind of work that needs to be done. So I'd like to begin by talking about the technology barriers or the technology challenges ahead. As I mentioned, the physical world changes very often. There may be robots that are moving. There may be people moving around, doors opening, light may change, a whole variety of different changing conditions. And what this can cause is a lot of disturbance and poor tracking. So we need to work on more robust systems that are tolerant of the changing conditions in the manufacturing environment. Furthermore, as you saw in many of the photos, there's a lot of markers, or what we call fiducials in augmented reality, that are used. And that's because for this to be very helpful, we need to have precise alignment. And the computer vision without the fiducials may not be sufficient. Despite great efforts and improvements in edge-based tracking and intelligent models that can find the edges in the physical world. I mentioned at the beginning that digital manufacturing encounters many problems in collaboration, or produces some kinds of problems in collaboration. I think technology that can help people at a distance collaborate on a task to achieve it more quickly or with fewer errors is a domain that is very, very interesting and will receive a lot of attention. Also, augmented reality doesn't work all by itself. It needs to be integrated within larger procedural systems. In some ways, this is a business issue, but it's also a technical issue when you're talking about data types and where those data sources may be, the security around them, the size of the model may be too large for the mobile device that you're trying to send it to. And there may need to be changes in the workflow to accelerate the procedures because you have augmented reality to help you. Well, that may be all well and good as long as the battery life the battery stays going. So we know that augmented reality, especially vision-based augmented reality, is very demanding on the processor and on the battery. In many of the examples I shared with you, you saw displays. And this is one of the very challenging areas, is the choice of the display, the positioning of the display, whether it can be mobile or can be positioned and mounted in a stationary manner. We often use tablets today for prototyping because they're very inexpensive. But as I mentioned, when a person has to do a procedure and they need both of their hands, tablet is not ideal. There are other factors that can come into play. There may be problems with the lighting may not be sufficient, or the tablet may drop, so it has to be ruggedized. There are, of course, many people studying how to use glasses or head-mounted displays in manufacturing, but these present new issues like, have they been certified for the environment that they're being used in? Do they permit the user to see all of the things around them without any obstruction or without risk? And wherever you have displays, you might also be thinking of a projector. We saw several examples of projection technology. That's very good for 2D, but it has some drawbacks. Wherever you use displays, you need to make sure that they are exactly calibrated and that they are synchronized with the sensors that the augmented reality is using. As I mentioned, solving the technical problems might introduce new business problems. And if you solve the business issues, you might have an impact on the choices that you make in the technology realm. So it's very important to keep in mind that there are changing and very rigid security policies. Very often in a manufacturing environment, the factory is considered to be strategic, and people don't want cameras there. There may also need to be models that are updated. You don't want people using information that may no longer be fresh. So you have to maybe remove data off of the mobile device or make sure that the data that's being used is from a central source. And we want to avoid at all costs that there be perhaps any hacking or tampering of the data. Safety is an important concern for all businesses, and the policies around the changing environmental conditions, like is it safe to use this device in this environment? Also, sometimes with headwear or with a tablet, a person might not be able to see the full 180 or the full range of their peripheral vision. Companies have to work within and make sure that they meet the regulatory constraints dictated by their governments. And, of course, we don't want to be spending more than the benefits that can be measured. So the return on investment needs to be measured and it needs to be validated. Finally, I think that there are many cultural problems or challenges ahead. Just like in the consumer environment, people do want to trust the technology, but it's new. And so there are failures, and what if the batteries run out? And in some countries, there's also laws against recording the worker's environment. So video validation and compliance may conflict with the regulations. And there are many people who need to be retrained or trained to do things differently, and so they need some assistance and to be involved in that process for it to go smoothly. During this presentation, I've spoken with you about the human in manufacturing, and I've underlined how often and how important humans and people remain despite the rapid sophistication of our information technology. AR is also an increasingly important mix. It's a component of the mix. It's the way we visualize the physical world and the digital world. It's an interface between those two. So it can be very valuable as we enter and we expand this Industry 4.0 or this next industrial revolution. In controlled conditions, companies have shown that today's commercial AR hardware and software is very good for what it's asked to do. It can help people be less confused, be more proactive, more organized, and have fewer errors, and also be able to maybe streamline the procedures that they use, and the processes that are very complex initially can be simplified. This is the end of the prepared remarks that I have for today. I'd be happy to take any questions if you have posted those for David. David, do we have any questions?
Christine, we do. We have about 7 minutes left, and we had 4 questions come through. So I'm going to go right down the line in order with the first question that asks, Christine, you mention automotive industry examples frequently throughout your presentation. Is there something special about automotive that makes AR more popular in this field?
It's very perceptive of you. Yes, many automotive companies have been involved. One of the reasons, I believe, is because of the strong and early support of the German government and the leadership shown by several people within that industry in that country. So it's a long evolution, and the examples that they are able to show us and the proof points that they have today are very much around automotive, but those can be applied to other industries. So it is true that there are many examples and many valuable research projects that have been done in that industry, and that can be lessons for us and be applied elsewhere.
Thanks, Christine. Question number 2. Why are there not a lot of hands-free displays seen in the manufacturing case studies that you featured in today's webinar?
Well, the photographs that I'm able to share with you are from real pilots and real prototypes. And so those have been in place for some years, or relatively, they've matured, and people are now working on new projects. And that's what makes them less sensitive for me to share with you. I think in today's manufacturing research and development environment, there are many, many hands-free displays or head-worn displays. The head-worn display is very important. However, it has problems of being too heavy. The battery life is too short for the time that the person is using it. The resolution and the alignment may not be sufficiently accurate. So there's certainly some challenges ahead, but it's extremely important and will play a very, very important role in the future. And there were some of those photographs and examples that I showed. They didn't show what kind of display the person was using, so it could just as easily have been a head-mounted display as anything else, a stationary or other mobile platform.
All right, going right down the line here, question number 3. One of our viewers today asks, I work in quality inspection for packaged goods. How would you recommend that I introduce augmented reality into our processes?
Well, that's very interesting. It's always good to know kind of who's joined us. I think packaged goods is quite different from those industrial examples that I've been showing you in automotive, aerospace, aviation, and naval engineering, and so forth. However, I think that there are some very good rules of thumb we can use. Look to see where the human is most critical and where the procedures are complex or very rare. So that's where I would recommend focusing your attention for a pilot. So you start off by taking all of the parts that are in the live production environment, bringing them into a laboratory, and configuring some of the procedures that you'd like to have a person follow using augmented reality outside of the production environment. Then to get feedback directly from people who are doing those procedures very, very often. They have great insights into where they need more assistance from the digital world. So I think turning to the people who are on the factory floor and getting their inputs is critical to success.
Very good, Christine. And the final question, this seems to be the last one from the audience, and then we can wrap up, is when do you think augmented reality in manufacturing will become commonplace? And thanks again, everybody, for joining.
Thanks, David. Well, that's a good question. I wish I had the answer to that. Augmented reality is already emerging, but getting into the production environments and having it be one of the things that people rely on every day is still several years, maybe as long as 5 years out. It depends a great deal on the industry, where they are geographically, and also the influences of the whole supply chain. One of the things I like to remember is when one of the very, very large big box retailers in America said it was going to start using RFID on all of its products. And it put a mandate on all of the suppliers to begin using RFID to track the merchandise as it was being manufactured, as it was shipping, and then where it was in the retail environment. So sometimes when one company establishes a policy and states that it will only work with companies who abide or who comply with certain procedures and use certain new technologies, it can have a cascading effect. And of course, everyone in the ecosystem and the supply chain needs to share in the cost of the research because it's very, very sophisticated, and it'll still take us several years. So thank you for your questions. Thank you for your participation. This concludes today's webinar presentation. Tomorrow, the discussion about this topic will continue. Join us for the next episode in our AR in the Future series on Friday, October 17th at 11 a.m. Eastern. The IEEE Standards Association is hosting a live Google Hangout panel discussion about augmented reality on the shop floor. A panel of experts will discuss the experiences they have with AR pilots. They'll share some success stories along with the lessons they've learned in trials. And in addition to the technical issues, I think you'll hear about cultural and business issues that are encountered. It should be a very lively and engaging discussion. Let's see you there. So tune in tomorrow and watch us on the Google Plus Hangout. For more information about viewing the playback of today's session or tomorrow's session, visit the IEEE Standards Association Google Plus page. Thank you again to the IEEE for giving me the opportunity to bring you today's webinar. Have a great day, everyone.